So let us look at the rotation curve of the Milky Way and the evidence for dark matter. This is a rotation curve of the Milky Way in blue, and what you would be expecting if all the mass was concentrated in the center in red, in the dashed red, that would be Keplerian orbits. The Sun is orbiting at this distance here with a speed of about 220 kilometers per second. That's the Sun's orbital speed around the galactic center. Later on, we'll discuss how the orbital speeds of the Sun and other stars are actually determined. But for now, let's just consider the implications of this orbital motion. The distance of the Sun from the galactic center is about 8 kiloparsecs. If we make an approximation that the Sun is on a perfectly circular orbit, we find that its orbital period then should be 2 pi times r over the velocity. So that gives you 50 kiloparsecs over 220 kilometers per second. It gives you about 0.2 gigayears. So during the Sun's 4.6 gigayear lifetime, it has gone around the galaxy center around 20 times. To find out how much mass is inside the Sun's orbit, we may use Kepler's third law. If the mass inside 8 kiloparsecs, the mass inside of the Sun's orbit is written in terms of the solar mass, then we have the semi-major axis in AU to the cube, and the period in years to the minus 2. So 8 kiloparsecs in AU, it's about a billion, 1.65 times 10 to the 9 AU, and the period 2.2 gigayears, like 0.2 gigayears. So 2 times 10 to the 8 years. If you do this calculation, then you find that the mass inside of the Sun's orbit is about 9 times 10 to the 10 solar masses. So 90 billion solar masses. So 90 billion solar masses is a lot of matter, of course, especially when you consider what the total luminosity of the galaxy is. The luminosity of the Milky Way is broken down into the luminosity of the disk, which is about 1.9 times 10 to the 10 solar luminosities, the luminosity of the bulge, which is about 2 times 10 to the 9 solar luminosities, and the luminosity of the halo, which is about also 2 times 10 to the 9 solar luminosities. So a grand total of then 2.3 times 10 to the 10 solar luminosities. So we have a luminosity of about 2 times 10 to the 10 solar luminosities and a mass of 9 times 10 to the 10 solar luminosities. The material then, which our galaxy is made of, must have on average a higher mass to light ratio than the Sun. Moreover, this mass contains only the mass that is inside the Sun's orbit. There is still the mass that is outside of the Sun's orbit. So we conclude that the galaxy has a higher mass to light ratio than the Sun. So that's one of the evidence for the existence of dark matter, matter that is not emitting light. So that's one way to determine the mass, by simply applying Kepler's third law if you know the distance of the Sun to the center and the period. We can use also a dynamical mass, assuming that stars and gas in the disk are on stable circular orbits. We require that the centripetal force is equal to the gravitational acceleration. And you can solve for the mass. Now, most of the galaxy's luminosity is provided by the disk, whose brightness falls off exponentially with a scale length of about 3 kiloparsecs. Most of the galaxy's luminosity is provided by the disk, whose brightness falls off exponentially with a scale length of about 3 kiloparsecs. So if here we have the Sun at 8 kiloparsecs, most of the luminosity is coming from about half of this distance, which should be about here. So if most of the galaxy's luminosity lies inside the Sun's orbit, if most of the mass also lies where the most of the luminosity is, we would expect that the mass would be highly concentrated, and then the orbits would follow more or less a Keplerian distribution. Now, observations of stars of gas clouds in our galaxy reveal that the orbital speed, in fact, does not fall off with distance from the center. That's what we're seeing here. This is the actual rotation curve in blue, whereas the fall that you would expect if all of the mass was concentrated in the center would be the red curve. All the way to the outer fringes of the disk, the orbital speed is constant, or even slowly rising with radius. Thus, there is more mass outside of the sun's radius than inside. At double the distance where the sun is, you estimate that the velocity is about 270 kilometers per second. So if we assume that the orbit there is circular and we use this estimate for the mass, we then find here 270 kilometers per second squared times 16 kiloparsecs over the gravitational constant. The mass inside the radius is about 3 times 10 to the 11 solar masses. So what is the density distribution that would give us a flat rotation curve? Well, it's simple to calculate. Let's go back to our expression for the mass. Now let's take the derivative of this with respect to radius and equate that to the continuity equation for mass conservation. So then you have here an equation for the density. The velocity is constant. So what you have is a density that falls with 1 over r squared. So this is a spherically symmetric density. It's a sphere surrounding a galaxy with the density falling as 1 over r squared in a region where the luminosity density is plummeting exponentially. So this is what it would look like. Galaxies should have a halo of invisible dark matter that is spherically symmetric with the density following as 1 over r squared. With this, you can fit the rotational curve. The solid line is the measured rotational curve. You have the contribution from the bulge, that's the long dashed line. Indeed, it is more concentrated in the center, gives you a Keplerian falling profile. The self-gravity of the disk, that's the short dashed line. And then the dark halo, the density going as 1 over r squared. That is the long short dashed line. You sum the 3 contributions, you have the total velocity. So the obvious question to pose is, what is this dark matter?